Okay, we're going to look at representations of functions as a power series. And we'll start with this function. Okay, this is a function that we know well. Let's draw the graph of it. Okay, so when x equals 0, we are here at 1. We have a vertical asymptote at 1. As we approach 1, we're going to blow up to infinity. And as x goes from 0 to negative infinity, then this is a positive quantity, so this is going to go down to 0. So it kind of looks like this. Let me change color. Looks like this. Okay, going off to infinity. All right, so what is important about this function? Well, this thing, as we all know, is just the representation of this power series. Or a better way to say it, this power series represents this function. Okay? And this is the start of the real stuff. The real big payoff from learning about series, power series, now is where we start to see it. So as a warm-up, we can just consider what this is actually saying. So let's write out the first few terms. Okay, equals 0, we have 1, then we're going to have x, then we're going to have x squared, x to the 3, and so on and so on and so on. All right, so let's look at this function over here. If we take the derivative of this function, what are we going to get? We're going to, by a chain rule, it's going to be 1 over 1 minus x squared. Differentiate the inner function. We'll have a minus, but the minus will cancel, and we will just get that, right? We'll just get that. That's the actual derivative. So in particular, at 0, we just get 1. So if we wanted to get the tangent line to the function at 0, so this is the tangent line I'm drawing right now. What's the formula for the tangent line? X, it's the slope at the point we're taking the tangent line, which is 0. So it's f prime of 0. X minus the point we're going through, which is 0. So it's just x minus 0 plus f of 0, right? This is the formula you're all very familiar with. We've just calculated f prime of 0 as 1. And so f of 0, again, it's 1. So what is this? This is just 1 plus x, and that's what it looks like on this picture, right? This seems to be the right thing. Okay, so that's the tangent line, and what does the tangent line do? It does a good job of approximating this function locally around the point 0 where we've taken the tangent line. That's the point of the tangent line. Okay, well, if we wanted to do a slightly better job of approximating, then we wouldn't want to have just a straight line. We want something which kind of curves upwards, because the graph does curve upwards. So a natural thing to try and do would be to define this function, q of x, which we'll define like this. And if we did that, that would do a better job. So when x equals 0, we agree, it's the same thing, but all it's doing is it's kind of putting a bend in this function, so it's kind of doing this. That's the same color. Let me do blue. It's kind of doing a bend like this. So this is our function q, and this function here is the tangent line t, right? So q is doing a better job of approximating it, and if we want to do yet a better job, well, if we continue q, since it's a quadratic, it would start to bend upwards like this, which is not what we see happening to our function. So if we actually took another term and put an x to the 3 term afterwards, that would start to account for the fact it's not bending upwards as we go to the left. So what I'm trying to say to you, and what I'm hoping is starting to become apparent, is that the terms we're getting when we do this kind of better and better approximation are exactly the terms of this power series, right? So these first two terms right here are exactly the tangent line, right? And the first three terms is this. Okay. So, what is this thing actually? Well, when does this representation hold true? We know that this power series converges for any x absolute value less than 1. So this will work from -1 to 1. Right here. And this again is 1. So what we have is something that is much better than a tangent line. We have an actual representation of our function as a power series over this range. So a tangent line is just a rough approximation to our function. Well, it's a so-called first order approximation to our function around the point we take the tangent line. This is incredibly more powerful. This is an actual interval where we don't just approximate our function, we completely recover it. So we don't have to deal with the function anymore, we can deal with this thing, which is a power series. And again, the power series, as I mentioned on the last lecture about power series, a power series is just as good as a polynomial for the purposes of everything we want to do. That's where this stuff goes. If we can, instead of dealing with a function, we deal with a power series, then a whole kind of treasure trove opens up for us, and that's what we're going to start to see today. Okay, so that's what's going on here, and the point of this particular chapter is just to kind of get a warm-up for that by trying to get representations of some simple functions that we can essentially get from this formula by just doing some algebra. So let's start with some examples. So in later sections, we're going to learn how to represent a massive class of functions. This is just the beginning of this story. So first example is this one. So let's take this function, 1 over 1 plus x squared. Now, this is not immediately obvious as something we can just use this geometric series formula for, but it's not also that hard, right? So if we just look at this, we can write this as 1 minus x squared, and then we can pretend that this thing in the bracket is our new x. So to be formal, we could let y be minus x squared, and then we have 1 over 1 minus y. And then we know what it is. So long as the absolute value of y is less than 1, then this is the sum like this. And then we can put back what y actually is. It is and there we go. That is our power series representation, so long as mod x squared is less than 1, but that is the same as just insisting that mod x is less than 1. So in this interval from -1 to 1, we can actually represent this function as this power series. Okay, cool. All right, so yeah, let's do another example. Try and squeeze it down here. This is the next example. Oops, x plus 2 as a power series. Okay. Solution, again, just do some algebra, right? So we'd like it to be the form 1 over 1 minus something. So let's write it like this. Let's factor out the 2, and then we're going to have 1 plus x over 2, which we can write as 1 over 2, 1 minus x over 2, and write this as 1 over 2, 1. Oops, no x here. No, there is. And then we're going to let y be this expression inside the bracket and expand it out. And I will do that after I clean the board. So we got to this point of writing as 1/2. Okay. So long as absolute value of x over 2 is less than 1, then we can write this as this power series. Oops. Right, and then we're going to pass this 2 through. And that's it. Okay. So in this particular case, this representation holds true for every x strictly between -2 and 2. All right, so even though it doesn't look that much like 1 over 1 minus x, just some simple messing around with the algebra gets us to that form. All right, let's do another example. What about this? All right, so remember that I said that a power series is just as good as a polynomial. Right? So if we look at this, it's almost in the form that we had before, except we have an x to the 4 in front. So let's write it as x to the 4 times 1 over x plus 2. But 1 over x plus 2, we already expanded, we know what it is. So this is like x to the 4 times this power series. And since it's just as good as a polynomial, if we just had a polynomial and it was the sum from k equals 0 to some finite number, then we would just multiply through the x to the 4. But we can do that anyway, because again, it's just like a polynomial. Whenever we actually have the power series converges, whatever you can do with the polynomial, you can do with the power series. So then this is the sum from k equals 0 to infinity minus 1 to the k, x to the k plus 4 over 2 plus 1. And that's it. Okay, and when is this true? This is true whenever mod x is less than 2. All right, so there's a whole bunch of exercises you have to learn to do where you have some expression and you will be able to quickly get out the power series when you find the algebra to turn it into something of the form 1 over 1 minus x or 1 over 1 minus x times something in front of it. These are not particularly hard problems. You do 10 of these things and then you'll be completely set. All right, now comes the real fire. So this is a very important result. Theorem. Given power series the sum from k equals 0 to infinity ck x minus a to the k with radius of convergence, which I'll abbreviate to R of c. Then the function f of x, which is defined to be equal to this power series. Okay, so for every x where mod x minus a is less than r, this thing does converge. It is some well-defined number, so we can simply define a function f of x to be that number. It's a well-defined function. And it's a function which is actually differentiable in that interval. In a minus r, a plus r, and further, and this is the key thing, we can differentiate it just like it's a polynomial, right? So if it was a polynomial, we just differentiate it term by term. The first term, k equals 0, is just a constant term, so that's just going to vanish. So we're going to start the sum from k equals 1 to infinity, and we're going to have k, ck, x minus a, to the k minus 1, okay? But not only that, and we can actually integrate this thing. We can find the antiderivative. So if we want to find the antiderivative of this thing, again, it's just like it's a polynomial, right? So if it's a polynomial, we would integrate it term by term. The constant term, k0, would turn into k times x. But since we're doing this around x minus a, we're going to write k0 x minus a. And that will just change the constant at the end, which we'll always have to introduce when we take the antiderivative. So what is this thing going to be? It's going to be the sum from k equals 0 to infinity. So doing this for each one of these terms, integrating each one of these terms, what are we going to get? We are going to get ck x minus a to the k plus 1 over k plus 1, and we have to introduce a constant c, some unknown constant, because it's the antiderivative. It's only defined up to some constant, okay? And both of these series converge in the interval a minus r, a plus r. Okay, so this is dynamite because this allows us to integrate any function that we can write as a power series and explicitly write down what the integral is. So as you'll see, we will have functions that were completely out of range for all the methods that we learned, and they will be accessible thanks to having this theorem. And this is not a particularly hard theorem to prove either. As everything, it's just pictures. However, these are pictures which are out of the scope of this course, because how does this work? Well, the moral is that a power series is basically like a polynomial. The difference between the power series and the polynomial is completely controllable. If this was just a polynomial, this theorem is obvious. We already know it's true. So showing that it's true for an actual power series is a matter of dealing with the difference between a polynomial and a power series and controlling that error. And that is just pictures, but it's pictures that that I can't show you because it's a little bit out of the scope. However, it really isn't magic at all. I wish I could explain this, but it really isn't magic. The moral is simply that the error between the series and the polynomial uniformly gets small. Uniformly gets small, so we can control it. And as we allow ourselves more and more terms, that error goes down to 0, and that's all there is. Okay. So if you are feeling confident about this subject, try and prove this for yourself. You'll find it's not hard. All right. So with this theorem, we can do stuff that we previously couldn't do. Okay, let's do this example. Let's try and find power series of this function. Okay. Solution. Well, right now we look at it and we realize there's no way to put it in some algebraic form of 1 over 1 minus x. Okay? But if we keep looking, we notice that if we differentiate 1 over 1 minus x, then by the chain rule, this power on the bottom goes from minus 1 to minus 2. We differentiate the inner function, and that'll cancel the minus on the top, and we get exactly that, right? In fact, we've seen this before, I think. Okay. And this thing here is something we can expand as a power series, right? And so let's call this thing star. So from star, we have that 1 minus x squared is the derivative of this power series, the sum from k equals 0 to infinity x to the k. Right? Because whenever absolute value of x is less than 1, then this thing actually is this power series. That's what we've seen. And by the theorem, we can then differentiate it term by term. So when k equals 0, the constant term vanishes. So the first term is just k equals 1. And then we go off to infinity. And we can have k x to the k minus 1. Minus 1. And that's it. And what is the radius of convergence? Well, the radius of convergence is needed to represent this thing as this power series, and it's true whenever absolute value of x is less than 1. So this is true for mod x less than 1. So, so long as mod x is less than 1, we can actually represent this function as this power series. Okay, cool. Pretty easy. Let's do another example. Log of 1 plus x as a power series. Okay, so what about this guy? Well, again, this is obviously nothing we can do with any algebra. We can't turn this into the form of 1 over 1 minus x. But if we look at it for a little bit, what comes to mind? Well, if we differentiate this, I wanted to change color, but that looks exactly the same. All right, let's try this. If we differentiate this, what happens? So d by dx of log of 1 plus x. And by the chain rule, we differentiate the top, we just get 1. And then we're going to have this, right? But then this thing is a power series, right? So this is 1 over 1 minus x. So this is the sum from k equals 0 to infinity. Minus 1 to the k, x to the k. All right, so we have that the derivative of the function we're interested in is the power series. So if we take the antiderivative of both sides, then we will actually have a representation of this, right? So taking antiderivative, so oops. We have the log of 1 plus x, and now we can use the fact we can integrate this thing term by term. So we're going to do sum k equals 0 to infinity minus 1 to the k, and then what is this? This will be k plus 1 over k plus 1 plus the constant of integration, constant c, right? But if we think a bit more, then what do we notice? Well, when x equals 0, log of 1 is just 0. All of these terms are positive powers of log, right? So when k equals 0, we have x to the 1 over 1, right? And then for all these other k onwards, these are all positive powers of x. So when x equals 0, this entire thing just drops and we just c. So since when x equals 0, the left-hand side is 0, the right-hand side has to equal 0. So actually this c is just equal to 0. So since log of 1 is 0, so c is 0, and that gives us the power series representation. And then we ask ourselves, when is this actually true? Well, it's true whenever this 1 over 1 plus x can be written as the power series. So that only happens when mod x is less than 1. So this is quite a different looking function. This is nothing that looks even close to being 1 over 1 minus x. Nevertheless, we have this guy as a power series. Cool. All right. So, what have we learned? So, we've learned that there can be some algebra that will turn things in the form of 1 over 1 minus x, so 1 algebra. Failing that, differentiate your function. Then after you do this, it can maybe look in the form of 1 over 1 minus x, then expand out that thing, the derivative of your function, then unwrap the procedure by taking the antiderivative. So get power series. Then anti-d, okay? Or we can integrate our function, or take the antiderivative, better to say it that way. It's the same thing, of course. At least for indefinite integral. And we've done those two examples. So in this particular case, this thing was not of the form 1 over 1 minus x, no matter what we did. We had our function, and the antiderivative of this function is 1 over 1 minus x. Okay? It's 1 over 1 minus x. And 1 over 1 minus x is actually a power series, so we can differentiate this power series and get back to the function we actually started from. So that was an example of 3. So this is 3. And in this case, we have something which again is not of the form 1 over 1 minus x, okay? But we can differentiate it and get it into the form of something which we can represent as a power series, and then we can take the antiderivative to get back to where we started. So that was an example of 2 right here. Okay, cool. All right, let's do another example. Okay, this example is super cool. So, example, approximate the integral 0 to 1 over 2 of 1 over 1 plus x to the 7 to within 10 to the minus 8. All right, solution. So if you just were faced with this problem before this particular class, you might think, okay, it's got to be something I can try here, maybe a u-sub, maybe some sort of trig substitution, something. But no, there's nothing. This is a very ordinary looking function. It doesn't look particularly bad, but none of the arsenal of tools that we've taught you does anything to this, right? So what do you want to do? Well, you can simply consider the tool we've just learned about. Consider using a power series. So how should we do this? Well, to begin with, this is of this algebraic form something like 1 over 1 minus x. So we're going to write this. distracted for a second. This will be minus 1 to the k, x to the 7k, just letting this be written as 1 minus x to the power 7. And this holds true so long as absolute value of x is 7 is less than 1, which is the same as saying absolute value of x is less than 1. Okay, and that's good enough because our actual range that we want to integrate is from 0 to a half, so that's certainly within the range for which this representation holds true, right? So that means that we can write this integral as the integral like this. And again, whenever we have a power series that converges, it is just as good as actually a polynomial. So if this was just a polynomial, we'd just integrate it term by term. So we're going to do this like this. K equals 0 to infinity, minus 1 to the k. And then we're going to integrate from 0 to 1 over 2, x to the 7k dx, right? And then what happens? Then we get the sum from k equals 0, infinity, minus 1 to the k, 0 to 1 over 2, and then we're going to have x to the 7k plus 1 over 7k plus 1. We put in the numbers, and we get this. Cool. And that's a completely explicit answer, but it is an alternating series. We don't actually know the value of this. We can't explicitly calculate it, and we are asked to actually come up with some particular number to within some particular error. But happily, since it's an alternating series, we know how to approximate this to within arbitrary small error, right? This was what we discussed before. So if we have an alternating series, so if S is this alternating series, k equals 0 to infinity, minus 1 to the k bk, and Sn was the nth partial sum, we know that Sn minus S is less than the size of the Bn plus 1 step, right? And we saw why this is true. This was this going forwards, then backwards, then forwards, then backwards, and then considering where we were on the nth step, and the fact that the next step is of size n plus 1, and we're always trapped between those 2 points, where we are on the nth step and where we are on the nth plus 1 step. So all that stuff we know very well at this point, and we're going to use it, right? So this is now just an alternating series. So our task is to find, which color? Let's do this one. So I'm going to write this as the sum from k equals 0 to infinity, minus 1 to the k, bk, where bk are these terms. Okay, so to get this answer to within 10 to the minus 8, then we need to find n such that the Bn plus 1 step size is less than 10 to the minus 8. Okay. And that is the same as asking that 7 n plus 1 plus 1 times 2, 7 to the n plus 1 plus 1. We want this to be bigger than 10 to the 8, right? So the smallest n we can find such that this is actually true is the number of terms we need to get this answer to within 10 to the minus 8. So then we do some plugging in numbers into our calculator. So if n plus 1 is equal to 4, then putting this into this, then we're going to have 7 times 4 plus 1, so it'll be 28 plus 1, which is 29. So it's going to be 29, 2 to the 29. So we're going to have 29 times 2 to the 29. And that turns out to be 1, 5, 5, 6, 9, 2, 5, 6, 4, 4, 8. Okay. And what if n plus 1 was just equal to 3? Then we'd have 7 times 3 is 21, plus 1 is 22. So we'll have 22 times 2 to the 22. And that turns out to be 9, 2, 2, 7, 4, 6, 8, 8. Okay, let's see which one of these works. So let's count up how many terms we have. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 terms right here. Okay. So this is definitely bigger than 10 to the 10. Right? How many terms do we have here? We have 1, 2, 3, 4, 5, 6, 7, 8. So this thing is less, therefore, than 10 to the 8. So if n plus 1 equals 3, that's not enough. But if n plus 1 is 4, that is enough. So this is good, and this is not enough. Right? Because again, what do we need? We need this. Okay? That's only going to be true if n plus 1 is equal to 4. That's the minimum we need. So the answer is, so to get this thing to within 10 to the minus 8, we need just to sum the term from k equals 0 up to k is equal to 3. So the sum from k equals 0 to 3 of minus 1 to the k, 1 over 7k plus 1, 2 to the 7k plus 1. This thing is our answer. This thing is our answer. Okay, so you might be thinking, well, you know, so what? But this is really a massive deal, right? So in the modern age of computers, it seems like it's just for free that we can answer these questions, that we can find out what a quantity like this is. But actually, no, right? This was something which we had no ability to do. We had no technological ability to answer this question before this technology. Right? There was just nothing that would allow us to get there. Before being able to write things as power series, before being able to integrate term by term, then this thing is inaccessible. None of the techniques that we've taught you will actually calculate this. And it could be that you are building your steam engine or your bridge or whatever, and the quantity you need to calculate is this quantity. Right? So what would you do? Well, you could just like plot points on a graph and make some approximation as best as you can, right? But that'll only get you so far. What if you really need the tolerances to be very close? What if you wanted to do more than build a steam engine? What if you wanted to, well, actually being a steam engine required you to get quite close tolerances just by that. What if you wanted to do something which is very delicate? What if you wanted to send a rocket to the moon? And you had something like this that you needed to know the exact answer for. Well, now you can do it. Now you can do it. Well, you can't do it in the sense of getting the exact answer, but you can get an approximate answer to within whatever level of error you want, right? And that's just as good as an exact answer. And indeed, that is the direction that modern math goes into. There's comparatively few things we can calculate exactly, but when we can get something which is approximate to whatever level approximation we want, that is just as good. That is just as powerful. So this is powerful. This actually allows us to calculate quantities that we would otherwise not be able to access, just with these rather, I want to say simple, geometrical ideas. These are ideas that allow us to do things in the world that were completely inaccessible before. This is not a game. This is not for fun. This is not just an exercise. Hopefully it is fun as well, but this has real power. So, this is the payoff, and this is what we're going to be able to do with a whole class of other functions as we learn more about power series. So this seems like kind of a technical topic. It might not be appreciated by all of you when you see it for the first time, but this is actual gold. This is really, really great stuff. When you are typing in your questions into Wolfram Alpha or Mathematica, and you're typing in some integral like this, they are exactly performing algorithms doing things like this to get the answer, or some other techniques from some subject called complex analysis sometimes. So this is how we can answer these questions. This is how we got out from the 19th century. We'd be making our industrial world with canals being pulled along by horses. Not canals, but boats on canals being pulled along by horses. So to actually build a modern world, you need to calculate things precisely, and stuff like this allows you to do it. And you start to get a flavor of this in this course. Okay, that's it.